Dear students, welcome to my channel. Today's topic is hidden Markov model, Viterbi algorithm for POS tagging. This is fifth video on this topic. I suggest you should watch all earlier videos for better understanding. In my previous videos, I have already explained generative and discriminative model of tagger. HMM model comes under the generative category. In this video, we are going to solve another problem for practice of Viterbi algorithm. Generative model. Here we want to determine the part of speech tag for x2 word. This is the states q1 and q2. q2 is the current state and here q1 is the previous state. We already determined the part of speech tag for the q1 state. Now we want to determine whatever the word comes out, that is nothing but the emitted from this part of speech tag, is belong to which category. Now we have that x2, so this is nothing but the state transition and this is nothing but emission. So here ambiguity is there. For example, this may belongs to the variety type of POS tags, so we just want to identify it belongs to the which category. q1 and q2 are states, x2 is a word which is emitted from q2 state. Hidden Markov model is nothing but the combination of state transition and emission. For state transition we are using the diagram, so here we restricted our discussion up to diagram. Here also we can go for the trigram, foregram also. And for emission probability we are using the Bayes rule. So basically the formula for hidden Markov model is probability of, what is the probability of POS 2 given the word and the POS 1. So we are determining the part of speech tag for this particular word x2 based on this and this. Therefore the formula of Bayes rule is probability of word given POS 2 into probability of POS 2 given POS 1. So this is bigram and this is nothing but the Bayes rule. Bayes rule data obtained from the emission probability and bigram data is obtained from the state transition matrix. Emission probability matrix. From a given corpus, identify unique tokens. Also identify total part of speech tag present in corpus. Assign correct part of speech tag for every token, because when we design the emission probability matrix and test transition probability matrix, it is nothing but the training of the data. So from the corpus we require to identify the correct part of speech tag and assign to into probability matrix, that is both emission and state transition. Arrange tokens in horizontal and part of speech tag in vertical fashion. We can change this order also. This will provide data for Bayes rule emission probability. For n token, m part of speech tag and size of the emission matrix will be n into m. State transition. Use the part of speech tag found from emission probability matrix. Create a size matrix of m into m. Use bigram concept and fill the entries in a table. This will provide the data for state transition probability. Once we make the label data set and when we enter the data into the emission and state transition, we can use the Viterbi algorithm of HMM to find out the part of speech tag for a given word in a very efficient way. Need of Viterbi decoding algorithm. It is based on dynamic programming. Dynamic programming breaks down the problem into sub-problem. It saves the result for future purpose, therefore no need to compute the result again. Now we will take an example. Here the corpus is given with the correct POS tag. So whenever corpus is given, we require to assign the correct part of speech tag, because this is nothing but our training procedure. Book a car, park the car, the book is in the car is in a park. So these four statements are there. So for example, the statements is given, the park is a book. So what is our job? We require to assign the part of speech tag for each word in a efficient way. Now here the book is can be verb and can be noun, and park is also can be verb or can be noun. So here the ambiguities are there. The park is a book, the is determiner, park may be noun, may be verb, is verb, determiner a, and book is again noun and verb. So here the ambiguities are present, whether park is noun or verb, whether book is noun or verb, and we just want to disambiguate this part of speech tag. The total number of ways are 4 possibilities are there. Viterbi algorithm is used to find the efficient path. So we don't want to trace all that 2 paths. We just want to efficient path from the start to end. Step 1. Assign correct part of speech tag to the training corpus. So for this problem we take a very simple solution. We take only 4 part of speech tag: verb, determiner, noun and preposition. Now for example, is comes under the category of auxiliary verb, but here it is taken at a very coarse level, so that is represented by the verb. Book a car. Now here book will represent verb, a is determiner, car is noun. Park the car, again park is verb, the as determiner, car is noun. So similar way we assign the correct part of speech tag to each word. Now here in comes as a preposition. So this is our first step, that assign the correct POS tag to the training corpus. Second, we require to create the emission probability matrix. Now to create the emission probability matrix, I have put this example so it is very easy for you to understand. Now what we require to find out the unique tokens. So book, a, car, the, park, is, in, they are the total words in our corpus. Now here we take only 4 part of speech tag. They are nothing but verb, determiner, noun and preposition. So we require to count how many verbs are there, how many determiner. So verbs are total 4, determiner are 6, noun are 6 and prepositions are 2. Now we have to check how many times book occurs as a verb. So book occurs as a verb only one time, so it is 1/4. Now book occurs as a noun how many times? So book occurs as a noun for one time, so it is 1/6. So in this way we require to assign the probability. For example, determiner A is occur as a determiner 2/6. So total 6 determiners are there, out of which A comes as a twice. So here A is as a determiner and again A as a determiner. So it is 2/6. So in this way we require to create the emission probability matrix. Next is the state transition probability matrix. That is our third step. Here we want to find out the transition between the states, because when we write the English, at that time certain rules are there. For example, generally the noun preceded by the determiner, then always the after the preposition there is a chances of the, even before the noun there is a chance of determiner. So these are nothing but the basic, and we are capturing all that using the state transition probability matrix. Now here it is the start of the statement and this is the end of the statement. Now here what we require to do, that how many times after the start the verb is coming. So start and verb is coming how many times? So verb, so 2/4. Then total this is nothing but diagram, that is count of wi minus 1 comma wi divided by count wi minus 1, means how many times the pair of wi minus 1 means start and verb, and after that divided by the count by start. So how many times after start verb is coming divided by the count of start. So that's why it is 2/4, because 4 times start of the statement is there. So in this way we require to write down. After that start and determiner, we can find out that total combination of start and determiner comes 2 times and divided by total count of start, that is nothing but 4. So this is same as diagram. So you should have the clear understanding of the diagram also to understand the state transition probability matrix. So in this way we complete the state transition probability matrix. Now here I can explain for the noun and the end of the statement. So how many times that after that noun and end of the statement divided by the noun. So in this way we require to do the things. Now the test data is the park is book. So here the ambiguity is present only between the two words park and book, and in this way we require to resolve this ambiguity and we want to find out the efficient path. Otherwise our algorithm is not efficient if we take all the possibilities. Now we will start with the first word start, and after the start the determiner start, because the statement is the park is book. So initial, this is the Q1 state, Q2. In Q1, that is the start of the sentence, this Q2 is determiner and the. There is no ambiguity because the belongs to only one category, that is determiner. So we will simply calculate the probability. Now probability of Q2, this is a common formula. Probability of Q2 given X2 and Q1 is equal to probability of Q2 given X2 given Q2 into probability of Q2 given Q1. This is the diagram formula and this is nothing but the naive Bayes formula. Probability of determiner given the word and the start of the sentence is nothing but the multiplication of emission probability at state transition. So we require to check from the emission probability matrix that how many times the and determiner combination takes place, that is 4 by 6, and how many times s and determiner, this is nothing but the previous word and this is the current word, so how many times combination of s determiner comes divided by the s, so that is nothing but 2 by 4. So 4 by 6 into 2 by 4 is equal to 1 by 3. So initial our probability is 1 by 3. Now we require to carry out this initial probability. Now the second word is park, and here the ambiguity is there, it may be verb or it may be noun, so we have to resolve that ambiguity. Now we require to consider the previous probability is 1 by 3. So now here two diagrams are there because we don't know the park belong to which category, noun or verb. Now we will calculate the formula for both, one is for verb and one is for noun, and we will check whose probability is more. Now probability of noun given park and determiner is equal to par, because this is nothing but our previous tag which we fix as a determiner, then probability of par given noun into probability of noun given determiner. So we require to check continuously emission probability matrix and state transition probability matrix to check the value, and we just require to multiply. So this is very important step to create a proper state transition matrix and emission probability matrix. So here we are getting the answer 1 by 18, and now we consider that park as a verb and we will calculate. Now here the probability that determiner after that verb and divided by the determiner, this combination is present for 0 times. So here the answer is 0. So sometimes it may happen that a particular path is very much efficient, but in between only in one of the two states, if value becomes 0, that all that significant path becomes insignificant. So at that time we can follow the smoothing also. So smoothing is nothing but not a very straightforward step that you should divide by that, but only you require to keep the condition that your answer should not be 0. So here answer is 0 because of this probability. So we are just multiplying with a very small number, that is 1 by 100. So we are getting the answer of 1 by 400. So better to go for smoothing, but it is not compulsory step. Even we can solve the problem normally, but when we do programming, at that time we can implement a smoothing in a very efficient manner, but manually it is very difficult to take all the possibilities. So if we want to apply the smoothing, only we require to multiply by a very small number, so it is 0.01, so it 1 by 400. So total answer we are getting, and after that we are again multiplying the previous probability, that is our 1 by 3. So 1 by 3, 1 by 3. So here answer is 1 by 18 and 1 by 1200. Now 1 by 18 is greater. So 1 by 18 is related to noun. So here we resolve that park as a noun. Now we can find out that whatever in our corpus, we always find out that park is a noun and the park is a verb also. But the position, the park is a book. So that according to position, now park becomes a noun. Now again there is a straightforward, we specify that is a verb. So next when we are taking here, now we specified that park is not noun, park is not verb but it is noun. So we are taking it is a noun, that becomes our previous state, that is Q1. Current word is, and that is, there is no ambiguity, it belongs to the category of verb. So there again straightforward calculation, we require to take the values from the emission and state transition probability matrix, and we are getting the answer 108. And remember that always we require to multiply the previous probability answer. So answer is 108. So here the answer becomes 108. Next is A as a determiner. Now A is again straightforward, it is determiner. So again it is the simplest step, and here we are getting the answer 1 by 6. We multiply with the previous step and we are getting the answer 1 by 648. Now for last word there is ambiguity, book as a noun and book as a verb. So we will write down that two diagrams, and we first calculate for the noun and after that we will calculate for the verb. Now here again that 0 is coming, so we again use that smoothing operation and we can see that, and we require to multiply with the previous probability answer. So after that previous probability multiplication, for noun we are getting the value 1 by 3888, and for that we are getting a very big value, that is very small number, that is 1 divided by 259200. Now obviously 1 by 3888 is greater than 1 divided by 259200. So our result is book as a noun. So in this way we resolve the part of speech tag ambiguity. Now result of the POS tagging after applying the HMM model is the is determiner, park is noun, is verb, A is determiner and book is noun. So in this way we we assign automatically part of speech tag to each word. So this is nothing but only practice problem for Viterbi algorithm. The references are Daniel Jurowski and Martin. Thank you.